St. Joseph's College for Women Autonomous Visakhapatnam, Department of Mathematics welcomes you for the online course on linear algebra. In this linear algebra, this section is inner product spaces. My name is Dr. V. Gauri Shankar Rao, Assistant Professor in the Department of Mathematics, St. Joseph's College for Women. In this video, objectives of orthogonality, orthonormal set and complete orthonormal set. Let us see this. What is the objectives? Orthogonality, it is a very important property in vector calculus and whatever it is. So orthogonality means understand the concept of orthogonality in an inner product space. So the product of two vectors, it is equal to 0, so opposite directions. So let us see this, the second one, interpret orthogonality geometrical as perpendicular. So this direction is moving on one side and this direction is moving on another side. The product always it is equal to 0. So verify orthogonality of vectors in real and complex vector spaces. Apply orthogonality to prove important results and to simplify computations involving inner products, projections and decompositions. So let us see this orthonormal set. So orthonormal set means it is a 1. So both vectors I equal to j, it is a 1. So not equal to means it is a 0. Define an orthonormal set as a set of mutually orthogonal vectors with unit length. Unit length means 1. Construct orthonormal sets from given linearly independent vectors, orthogonalization and normalization process. See this vectors is moving on the different directions. Use orthonormal sets to simplify inner product calculations. So ith component of V if the direction ui, establish linear independence of an orthonormal set. It is a linear independence means it is the summation of first into and second vector. You can add the total values, it is equal to 0. Orthonormal. So complete orthonormal set means it is a complete. Understand the concept of completeness in an inner product space. A set is complete if it spans the entire vector space. Once it is a spans, it is a total cubed, is a completeness. Identify complete orthonormal sets, orthonormal bases in finite dimensional inner product spaces. So E1, so on, En is an orthonormal basis of an n-dimensional space V. Express any vector as a linear combination of complete and orthonormal set. You can write as a linear combination in third vector and EA, then you can write summation. Apply completeness in solving problems involving expansions, approximations, least squares and Fourier series. So overall goal of this objective on orthogonality, orthonormal set, complete orthonormal sets, to develop a strong conceptual understanding and effective application of orthogonality, orthonormal sets and complete orthonormal sets and inner product spaces. Before going orthonormal sets, let us see this one more example problems on here. Alpha equal to, it is look like as a complex numbers related. Alpha is the 2 comma 1 plus I comma I imaginary numbers, and beta also vector in complex form. B 2 vectors and B 3 of C. Here the 3 means the 3 values is given. So or C cube, C means the complex numbers in 3. So compute the inner product alpha comma beta and norm alpha comma norm alpha and norm beta, at the same time norm alpha plus beta. Also verify Cauchy squares inequality and triangle inequality. In one problem they are asking the so many quotients. So for the first inner product alpha comma beta, the same pattern, the first term into the second always you can write like this. Okay. So after that you can apply the conjugate, or we can write the conjugate 2 minus I. Conjugate means imaginary number, you can write the plus. Okay, the normal number you can denote as the same, but as a complex numbers is given imaginary, you can conjugate means plus, it can be changed as minus. Simply you can remember that property, then you can multiply that equation, you got 8 plus 5i. Norm alpha square also the same pattern, you can take that alpha is the 2 times, then you can apply the product, you got the value is the 7. At the same time the norm beta square also, beta already is given now, 2 minus I comma 2 comma 1 plus 2i. The simply you can multiply that, conjugate 2 minus I into 2 minus I bar and 2 into 2 bar, it is like complex conjugate. Okay, so by using that conjugate, 2 minus I bar is given. How we can write 2 plus I? Here that 1 plus 2I, it can be written as 1 minus 2I. Thus you can multiply that I square value, already know that minus 1. So by using that I square equal to minus, you got the final value is a real number 14. The simply the product of the two vectors, the ordinary numbers and complex numbers, is given, the both are the same, but here you can apply the conjugate. So the first into second complex number is given, you can write conjugate. That is the most important point you can observe. Let us see this continuation. Alpha plus beta, again you can apply that plus. You got a complex number in vector 4 minus I, 3 plus I, 1 plus 3I. Now we can apply that norm alpha plus beta whole square. How we can write, see this, the complex number you can write conjugate, and this one you can write the complex number with conjugate. 1 plus 3I you can write the conjugate. So after that this conjugate you can change the negative to positive. The same pattern you can apply the second and third terms. Then you can choose multiplication, ordinary multiplication. I square value you can replace the minus 1. You got 37. So inner product alpha comma beta, again you can already know that alpha comma beta inner product 8 plus 5I. What is that? Normalized assembly is given root over first term square plus second term square. Here I square is a minus 1, that's you can write 5 square. So this value is the root over 89. So norm alpha into norm beta, already before slide you can find the norm alpha, norm beta, just you can take the product of 7 into 14, 98. So by the cos inequality, norm alpha inner product alpha comma beta less than or equal to norm alpha into norm beta. Again that same property parts well. So norm alpha plus beta equal root 37, norm alpha plus norm beta equal root 7 plus root 14. So less than or equal to. So both properties satisfies. So let us see this one more similar problem. But here that only they are asking standard inner product alpha comma beta and norm alpha comma norm beta. They are given as two complex numbers, two complex vectors. They simply can remember that already I said 1 minus I into 2 minus 5I. The both are the complex numbers, you can write as conjugate 1. So 2 plus 3 into this one you can write as conjugate. Once the conjugate, how we can write imaginary, it can be changed as negative to positive, and this one also negative to positive. Then you can apply the product. The finally you got 10 plus 4I. The same pattern you can take the norm alpha square, the same formula applicable. So after that conjugate changes negative to positive, positive to negative. Then you can apply the multiple property. You got 1 plus 1 plus 4 plus 9 equal to 15. So norm alpha square value is 15, but norm alpha equal to root 15. So again norm beta square equal, norm beta square means you can take that complex numbers in beta related. So you can apply the conjugate second term. So conjugate, again you can change the negative to positive and imaginary negative to positive. Then you can apply the product. So you got 4 plus 25 plus 9 plus 1 equal to 39. So 39 value is the root norm beta square formula. So the norm beta equal to root 39. The similar problem, it is very important in bit parts. So let us see this. Let us see this. If alpha comma beta are two vectors in unitary space, then find norm alpha plus I beta and norm alpha minus I beta. So norm alpha plus I beta whole square equal to norm alpha plus I beta whole square. How we can write alpha plus I beta comma alpha plus I beta. So like norm alpha square equal in the product of alpha comma alpha. So by using the same property, the first alpha into the second total term and I beta into the second total term, I means treated as like constant outside of the imaginary. And then you can apply again the multiplication of first and second. Okay, I you can write as I bar, and here also you can write I into inner product beta comma alpha, and this is I into I bar beta comma inner product beta comma beta. So first and second term as it is, and third also as it is. I into I bar, it can be treated as 1 and the beta comma beta. So inner product alpha comma alpha, we can write norm alpha square and the second as it is term. So can I write beta comma alpha conjugate alpha comma beta. So this one also norm beta square. So norm alpha plus I beta whole square equal to, it can be written as norm alpha square minus I into alpha comma beta plus I into conjugate alpha comma beta plus norm beta square. So the same property you can apply alpha minus I beta also. So but here one more thing, remember that minus I should be common. The remaining procedure as it is. Inner product alpha comma alpha, it can be written as norm alpha square and it can be written as conjugate, it is a plus I, and there is no conjugate, that's why we can write minus I as it is. Beta comma alpha can I write symmetry property conjugate alpha comma beta. So therefore norm alpha minus I beta whole square, it is nothing but norm alpha square plus I into inner product alpha comma beta minus I into conjugate alpha comma beta plus norm beta square. Let us see this one more problem. If alpha comma beta are two vectors in unitary space, then prove that inner product alpha plus beta comma alpha minus beta equal to 0. The same already you proved alpha comma alpha equal to, what is that? You can prove norm alpha square equal to 0. In the time alpha equal to 0, the same property. Norm alpha plus beta whole square equal to norm alpha plus beta whole square equal to, how we can write alpha plus beta comma alpha plus beta. Let us see this. The first alpha into this total term second. So next beta into the total term alpha plus beta. Again multiplication, you can see this observation, first and second. Here also then first and second. After that norm alpha into alpha square, inner product of alpha comma alpha, we can write norm alpha square. And this one alpha comma beta and as it is second and third term as it is, inner product beta comma beta equal norm beta square. It can be written as equation 1. So after that again alpha minus beta, norm alpha minus beta whole square, again you can apply the same property multiplication. You got the simply plus is replaced by minus. So this is a equation 2. Now we can 1 minus 2, you can do the 1 minus 2. So what is the 1 minus 2? Alpha norm alpha plus beta whole square plus alpha minus beta whole square. Then you got the plus to minus symbols is a cancel. Actually this is not a minus, it is a plus. Both you can add 1 plus 2 equations. The negative value should be cancelled. Finally the first terms alpha betas, 2 alpha plus betas, and the second one is conjugate 2 alpha betas. So automatically 4 real numbers alpha comma betas. So let us see this. This is the minus only. Okay, it is a correct. This is a minus only. So once you can take the minus, the plus symbol should be cancels, and this one is a minus. It treated as like plus. Then it is like 2 into alpha comma beta plus 2 into conjugate of alpha comma beta. It can be written as 4 into real of inner product of alpha comma beta. This is a simple problem on unitary spaces in complex. Let us see this orthogonality. Orthogonal vectors. Let alpha and beta be two vectors in an inner product space V. Then alpha is said to be orthogonal to beta if inner product of alpha comma beta equal to 0. It means what is that? The two vectors is in inner product space. Then alpha is said to be orthogonal. It means inner product you can show it is a 0. So that is orthogonal to beta. Inner product of alpha comma beta equal to 0. So alpha comma beta, it is a conjugate alpha comma beta equal to, both sides you can apply the conjugate. So once you can both sides you can apply the conjugate 0, always it is a 0. Conjugate alpha comma beta, how we can write inner product of beta comma alpha. So automatically beta is orthogonal to alpha. Okay, alpha is orthogonal to beta. It is like symmetry property, beta is orthogonal to alpha. Why? Because of the product is the 0. So let us see this one example. Alpha is a 0 minus 2 comma 3, beta is the 7 by 2, 3 comma 2. Just you can apply the multiplication on this, the final product equal to 0. It means it is a orthogonality. Not equal to 0 means the two vectors is not a orthogonal. Once 0 comes, it is a orthogonal. So let us see this one more example. F of t is given 2 sin phi t and g of t is given cos phi t in between integration 0 to t. So once the polynomial equation is given, you can take like this: f of t conjugate g of t dt, 2 sin phi t and cos phi t dt. Okay, so it is look like as a 2 sin a cos b. 2 sin a cos b equal to what is that? Sin 2a. So sin 2a, it means sin 2 phi t. So sin 2 phi t means it is integration minus cos 2 phi t. Internal derivative is the 2 by as a denominator. Now we can sub the upper limit and lower limit. Here you can observe this cos n phi equal to minus 1 power of n. Cos n phi equal to minus 1 power of n. By using the property, the total value equal to 0. Once the 0 it comes, it is the orthogonal vectors. These are the simple examples of orthogonal vectors. The product of two vectors, it is the zeros. Let us see this the note point. The 0 vector is orthogonal to every vector. Finally, orthogonal means what is that? You need the 0. Once you can take 0 vector in anything vector, product equal to 0. The 0 vector is the only vector in V which is orthogonal to itself. that is alpha is orthogonal to alpha equal to inner product of alpha comma alpha equal to 0. So alpha is orthogonal to alpha implies inner product alpha comma alpha equal to 0. Once inner product it is a 0, alpha equal to 0 vector. Let us see this orthogonal set. Let S be a non-empty set. Non-empty set means the compulsory the vector should be introduced. The set of vectors in an inner product space V, then S is said to be an orthogonal set if every pair of distinct vectors are orthogonal. So orthogonal set means if every pair of distinct vectors are orthogonal. So let us see this alpha I, alpha j equal to 0. The both vectors should be different. In the time it is the 0. So let us see this alpha I, alpha j not equal to 0 for I equal to j. The both vectors should be same. In the time it is not equal to 0. The both vectors is a different, it is a 0. Both vectors is the same, it is not equal to 0. It means orthogonal set. Let us see this orthonormal set. Let S be a non-empty subset of an inner product space V of F. Then S is said to be a orthonormal set. So before when this one is a small difference, so let us observe this. Alpha I, alpha j equal to 0 for I not equal to g. So before one is a I not equal to j, it is a 0. Here also I not equal to j, it is a 0. So alpha I, alpha j equal to 1 for I equal to j. Both vectors equal to same. In that time it is a 1, but it is a 0. So that is a small difference between orthogonality and orthonormal set. So let us see this in the note point. An orthonormal set in an orthogonal set with additional property that each vectors of length 1. That each vectors of length 1 is additional property. An orthonormal set can't contain 0 vector. So orthonormal set can't contain 0 vector. Every inner product space has an orthonormal subset. Every inner product space has an orthonormal subset. So once the space is given inner product, automatically it is an orthonormal subset. Let us see this theorem. The vectors alpha comma beta of a real inner product space V of F are orthogonal if and only if norm alpha beta whole square equal to norm alpha square plus norm beta square. Alpha beta are the real inner product space V of F. But once it is orthogonal means what is it? It is the product is a 0. But what they can say if and only if similar norm alpha plus beta whole square equal norm alpha square plus norm beta square. Let us see this. The first you can consider and this one. Norm alpha plus beta whole square equal to LHS equal to RHS. Okay, so norm alpha plus beta whole square we can write inner product of alpha plus beta comma alpha plus beta. It is equal to norm alpha square plus norm beta square. Again the same multiplication property inner product alpha into the total alpha into alpha and alpha into beta and the second beta into alpha and beta into beta. So the right side as it is. Inner product of alpha comma alpha means what is the norm alpha square. So beta comma alpha can I write conjugate alpha comma beta and this one also norm beta whole square. So let us see this the property norm alpha square and norm beta square. Okay, norm alpha plus beta square, then you can shift the right side, it is the 0. So after you got only second and third terms, it is visible. So then inner product alpha comma beta plus the conjugate can I write alpha comma beta. So therefore two values the same, 2 into alpha comma beta equal to 0. Then inner product alpha comma beta equal to 0. Once the product equal to 0, it means what is that? Orthogonal vectors. So alpha gamma beta are the orthogonal vectors, automatically the product is the 0. So therefore the theorem is proved. Let us see this one more theorem. In an inner product space, any orthogonal set of non-zero vectors is linearly independent. So linearly independent means we can say it is a 0. So let S be a finite or infinite orthogonal set of non-zero vectors in inner product space V of F. SB is the finite or infinite orthogonal set of non-zero vectors in an inner product space V of F. So automatically what they said, alpha vector it is not a 0 vector and the second vector it is not a 0 vector. The product always it is the 0. Why? Because of the both vectors is the different. So let us see this. S is the one set numbers alpha 1 alpha 2 so on alpha m be a finite subset of S having m distinct vectors. So for example you can take that finite values. Let us finite. So there exists a1 a2 so on am belongs to AF. such that a1 alpha 1 plus a2 alpha 2 plus so on am alpha m equal to 0. The product of the two vectors, some summation property you can apply, it is a 0. Now we can prove that a1 equal to 0, a2 equal to 0, so on am equal to 0. The first a1, a2, am equal to 0, then you can show that. So automatically 0 multiplication anything vector is called as a 0. Now 0 vector alpha equal to 0. Why? Because of the first 0 anything multiplication is a 0. So already that a1 alpha 1 plus a2 alpha 2, okay, so on am alpha m into alpha I. So automatically it is the 0. Why? Because of this total value already you proved it is the linear independent, it is a 0. 0 and anything is the 0. By using that, the product a1 alpha 1 and alpha I, a2 alpha 2 and alpha I, the so on again. So here you can take that a1 is the common, you got alpha 1 alpha 1, here a2 is the common, alpha 2 alpha 1, here you can take that a is the common, alpha I, same nth term you can take alpha m alpha I. So it is inner product, it is a 0, and this one also 0, and it can be written as norm alpha I square, and this one is 0. The both different, automatically it is a 0. So by using it is nothing but a norm alpha I square equal to 0, automatically you can shift the right side, a equal to 0. So therefore a1, a2, so on am equal to 0. So the set S is linearly independent. Why? Because of the total value it is equal to 0. Every non-zero finite subset S1 of S is linearly independent. Therefore S is linearly independent. The product, for example, a1 alpha 1 plus a2 alpha 2 so on an alpha n equal to 0, in that we can show a1 a2 so on an equal to 0, automatically it is a linearly independent. So let us see this the theorem. Let us see this theorem. Let V of f be an inner product space and S equal to alpha 1 to so on alpha n be an orthonormal subset of V. If beta belongs to alpha s, then beta equal to summation I equal to 1 to n inner product beta comma alpha I into alpha I. So let us see this. V said it is inner product space, but space is the S is relevant to alpha values, orthonormal subset of V. They can say it is orthonormal subset of V. So then you can put beta equal to the summation of beta alpha I comma alpha I. Let us see this. Given that S is an orthonormal set, already they said that S is the orthonormal set. Once it is an orthonormal set means what is that? The both vectors is a different, it is a 0. So both vectors is a similar, the unit vector it is equal to 1. That one is a property, orthonormal set. Again they said it is a beta belongs to L of S, linear subset. So beta means what is that? a1 alpha 1 plus a2 alpha 2 plus an alpha n, linear. So then now we prove that beta equal to the combination of summation I equal to 1 to n beta comma alpha I into inner product of alpha I. Let us see this. The first you can take inner product of beta comma alpha I. Beta comma alpha I equal to, beta means already know that a1 alpha 1 a2 alpha 2 so on an alpha n. So then you can take the product alpha I. The simple a1 is outside of the inner product, you can multiply alpha 1 into alpha I. The same pattern you can follow the up to nth term. So then inner product alpha comma alpha equal to 0, it means norm alpha square equal to 0. By the condition it is a 0 and this one also 0. The finally this ith term is there. Why? Because of we don't know what is the ith value. So a into alpha I norm alpha I square equal to ai. Here norm alpha I square equal to what is that? By the orthonormal set it is a 1. So that's why a into 1 ai. So therefore beta equal to a1 alpha 1 a2 alpha 2 plus 1 an alpha n equal to, can I write summation I equal to 1 to n ai alpha I. So this is equal to summation I equal to 1 to n beta comma alpha into alpha I. See this one small problem. It is like numerical values. So that 1 0 0 0 1 0 0 comma 0 comma 1 is an orthonormal set in the inner product space V3 of R. So what the given vectors you can consider, one is the E1 and the second vector is E2, third vector is the E3. By the property can I write orthonormal means what is the root of first term square plus second term square plus third term square, it can be written as 1 1 1. Normal E1, normal E2, normal E3 values is the 1. Now we can take the product term. So orthonormal means what is that? The product equal to 0. The first vector into second vector it is a 0 and second vector into third vector into 0. First and third vector equal to 0. The total vectors should be zeros. Automatically the given three vectors is an orthonormally set. The simply the three vectors is given. First and second vector product is a 0. Second and third vector product is a 0. First and third vector product is a 0. Automatically the given three vectors is the orthonormal set. So if anything is not equal to 0, it is not a orthonormal set. Remember this point. Thank you all watching this video. Thank you.